Okay, so then that means that the voltage across all three of our resistors, the total voltage, is the sum of the voltage across 1 plus the voltage across 2 plus the voltage across 3. Just like the total height is the sum of the height difference between each one of our slides. Trying to make an analogy. Okay, so now if V equals IR, let's make a substitution into this voltage equation right there. So the total voltage would be the current that flows through times the total or equivalent resistance. Usually EQ is used to mean equivalent resistance. That's what I think your textbook uses. All right. Then V1 would be the voltage across that first resistor. It has the same current I running through it times R1 plus V2 would be what? I times R2. And V3 would be I times R3. So since the current that goes through the whole circuit is the same as the current that goes through each one of my resistors, can't I divide by I on both sides? Yeah, so now the equivalent resistance of this series of resistors would be what? What do we do to the resistors to find the whole total? You just add them up. That's right. So it is the sum of all R sub n, I guess you'd call it. Isn't that right? Sum of all the resistors. And you like a box? So I'll put a box around that. It's a symbol that means I'm going to sum up all of the resistances, and little n represents, 1 and 2 and 3 and 4, because we could have 20 resistors in series. Okay, so just R sub n. Okay, so the total voltage across all of the resistors that are in series with each other, summing up to be that whole voltage, that's a rule for voltage in series. Okay? And I's are the same. I equals I1 equals I2 equals I3. If you like to put those rules on there too. That's the current rule for resistors in series. All right, so resistors in parallel look like this. Usually there's a wire that comes into a junction, and then it branches off, and there's a resistor here, a resistor here, and there's no rhyme or reason how many little squiggles you need to make. You can just make a few little up and down squiggles like that. I'm going to connect all these and then have a wire leaving the junction. And these resistors could be the same or they could be different, so I'm just going to label them R1, R2, and R3. So these are like parallel water slides. You know when you're at the water park and you climb up the stairs and you get to the top, and you can go down like slide 1 or slide 2 or slide 3, but everybody ends up at the pool at the bottom? Okay, so that's the way resistors in parallel are kind of behave. Now, remember, if height is kind of like voltage, does everybody go through the same height change if we all climb up the tower and we all end in the same pool? Yeah, so what can you say about the voltage then? If voltage and height are kind of analogous, what can you say about the voltage across each one of these? It's the same. So then this voltage would just be V, this voltage would be V, this voltage would be V, those are commas. And so then the voltage from here all the way, I'm just going to draw a little line, all the way to here would also be V, because that's that's ultimately the height difference between here and the bottom of the pool. Okay, that height difference is the same as the height difference of each one of my little